Today we are going to learn something about Ito calculus, that is how do you write say a Taylor's expansion in Ito for Ito's integral. Now you see quadratic variation will always add some extra term. For example, for the moment just think that you have function f wt and assume that wt is differentiable, which you know that it is not, but just for the heck of it. So just to gain some insight. So if you take a derivative, it is exactly equal to, if you use a chain rule, then it will be f dash of wt into w dash t. Okay. Now you know that this is not really true, you cannot have f w dash t. So you can write d of f wt is f dash wt into w dash t dt. If you go by the standard way of doing differential calculus, this actually symbolizes the differential of t, and so you will write though we know that we have been able to give some meaning to dwt, but we really have not done, this is not really the job. But as we will show that if we can give meaning to this, and if we can give, because we have given some meaning to this dwt, in actual case this expression does not end here, but a term is added because of the quadratic variation. So in Ito's sense, this actually means assuming that f is nice enough to be twice continuously differentiable, this is what you will get. Instead of getting this, which you get if you are thinking in terms of standard calculus, and this is what you get as a stochastic calculus. This equation is often called a stochastic differential equation. This equation is often called a stochastic differential equation, or SDE. So I will write down what is the full form of SDE. It is called the stochastic differential Now, I would just want you to recollect a few facts. So, one of them, you know that the quadratic variation of a Brownian motion is path independent. A shorthand, short form of writing this. So this is the actual process, but we are writing it in a short manner. This is shorthand. Don't think that, don't immediately try to attach meaning to this. So this is just way of doing the math, it's not. Similarly, if you take dt times dt, quadratic variation of t, it being a normal function, you know that will be 0. And then if you take a cross variation between wt and dt, that is dt in dwt into dt, that is also 0. So this is a basic shorthand that you should remember when you are going to study finance or do derivative pricing. These are very basic shorthand, very basic shorthand. Now this SDE, what you see here is actually a shorthand. This SDE is a shorthand of the following. Suppose I integrate from 0 to capital T, I can integrate it out if you think in terms of standard integration, then it is a shorthand of the following, or 0 to small t. So this one, this SDE is a shorthand of FWT minus FW0, which is essentially giving you this is equal to integral 0 to t f dash wt dwt, which is an Ito integral for which we have clearly shown how to think about it, plus this additional normal integral. So, this becomes an Ito's expansion, Ito's calculus. So, basically you can rewrite it as f of Wt is equal to f of W0 is equal to f of W0 plus 0 to t f dash Wt dWt plus half of 0 to t f double dash Wt dt. Now, Ito's formula, which is also called the Ito-Doeblin formula in Shrieve's book, can be done at a slightly general level, where you take a function of two variables. So, I will now write down Ito's formula for two variables. So, Shrieve also calls it the Ito-Doeblin formula in the name of another young young researcher who possibly died in the World War, but in the World War II, but he also had almost got the same, came to the same ideas. So, whichever you want to call it. I think I found this Ito-Doeblin thing only in Shrieve's book, everywhere it is been called Ito's formula. So, we will just go by the traditional name Ito's formula. So, let us see what does Ito's formula tell us. Ito's formula tells us the following: it considers not a function just of t, just of Wt, f of some function of a process, but t and Wt, but t and a process. So, ftx is a given function, x is in R, t is in R, right, is a given function. Okay. Then to fx tx, that is the partial derivative with respect to x, ft tx, that is partial derivative with respect to t, and partial derivative with respect to everything else, partial derivative with respect to xx, one is second order partial derivative, these exist and are continuous. Now, exist means exist finitely. Now, once these things are done, what formula we have? Once these things are given, we get the following formula. So, Ito says then for every t greater than equal to 0, we have the formula f t w t is equal to f 0 w 0 plus 0 to t ft t wt dwt, sorry, ft t wt dt. See what happens, only when I take the partial derivative with respect to x, I will consider e to integral, because the random process is at the in the place of the x variable, plus 0 to t f of x t wt dwt. Then there has to be the correction term to the quadratic variation. Okay. So then that will be 0 to t f x x t w t and dt. So it will not, this will not be an e to integral, so this will be an e to integral. So finally you are talking about a stochastic process. Now what we are going to do right now is to, instead of trying to prove this whole thing in a very general setup, we are going to look into the very simple case of f being half x square. We will forget the fact that the t variable is also included. We will not take the t variable, we will just leave the t variable and try to deduce a formula like this. When I have something f is half x square. So our job now would be to consider a function fx is equal to half x square and show that this actually holds. So that will give you a fairly good idea about how to proceed. So let us fix t greater than 0 and then do a partition and proceed. But before that, you realize that for a quadratic case you have an exact second order, Taylor's expansion. So if you have f of xj plus 1, it is f of xj plus f dash xj, xj plus 1 minus xj plus half of f double double dash x xj. The higher order terms will all vanish, there will be 0 higher order derivatives. That will be the Taylor's expansion. So can we use this idea now to proceed? That is the idea. So again you will start with the interval 0 to t, and I will consider a partition, given partition where 0 equal to t naught less than t1 less than strictly less than tn equal to t. And as before, we will consider the norm of the partition is the maximum value of the length of the intervals. Right, it is a nth interval, you could have large, right, I am just writing like this. I am not giving n, possibly should have given n. Okay, I will just take the partition norm goes to 0. So this partition norm is max t I plus j plus 1 minus tj, where j goes from 0 to n minus 1. So this is the basic preparation that you take, and then once you take this preparation, you start working on it, trying to prove this formula. So let us keep this formula on the side and try to see how do we arrive at it. But then, so let me just remove everything and then start to prove this. So once I prove this formula, you just accept this formula as correct, because it will be too complex to go and work it out. It is better to get a feel of it, because this is many people for this is the first course in stochastic calculus, rather than going into every detailed rigorous steps. Math can be sometimes understood with too much of rigor built in for the first time, and then you increase your levels. So now, if we take the partition, then let me look at this. This is nothing but the collapsing sum, W0 is 0 anyway, the collapsing sum. So I have forgotten the T, I have not taken T, F is half x square. The summation j is equal to 0 to n minus 1 f of W Tj plus 1 minus f of W Tj. This is what you have. Now, if I think that this is just this expression f x j plus 1 minus f of x j is a quadratic expression half x square. So, f of W t is half W t square. So, I am just using the Taylor's expansion at this point, nothing else. The Taylor's expansion which you have known here. So, you know because of the higher derivative is going to 0, this is the exact Taylor's form, Taylor's expansion. Thus, I can write just for each of them I am writing, so I am finally writing the sum also. So, f is a continuous function. Now, if I go by f dash of x, which is x. So, this is nothing but W t j, sorry I made a mistake, because this W t j is the argument of the function f now. So, that is playing the role of x j plus 1, W t j plus 1, please correct it. Now, what is f dash of x? F dash of x is x. So, f dash of W t j is W t j. So, W t j is a real number, so it does not matter. So, it is W t j into W t j plus 1 minus W t j, and when you take the second derivative, it is 1. So, it is half of summation j is equal to 0 to n minus 1 f dash W t j sorry, f dash W t j is just 1, f double dash W t j, because that is the expression of that is the value of the second derivative. It is 1, so 1 into W, you can immediately realize what has happened. So, if I go and take the limit as j as the norm pi goes to 0, this would represent an Ito integral of W, and this would represent the quadratic variation, right. And so, what does this represent? So, as norm pi goes to 0, f of W t, because this is not depending on that partition, this is independent of it, these are the two endpoints. This will be nothing but 0 to t W t dW t, the Ito integral plus half of the quadratic variation. So, it will be WW of t. So, basically it will be 0 to t Wt dWt plus half of t. Okay. Now, how do I semblance with this? What is Wt? Wt is nothing x, which is f dash Wt. So, it is 0 to t f dash Wt dWt. This is one thing, and then you have to realize that what I can write, half of 1 into t. What is 1? It is f double dash Wt. So, I can write this as half of 0 to capital T f double dash Wt dt, sorry dt small t. So, you see finally I have got this formula by using the fx. So, I have to choose, if I choose a particular f, I can get a particular formula. So, I chose f equal to something, and then you see it matches this formula, fx equal to x square, and it matches this formula. So, under this fx equal to x square, we have proved that I can write it like this, or else in general when you take a function f tx, you have this formula. You can ask, what about fxt and ftx? So, because you see when you do fxt and ftx, you are doing this cross variation, that will become 0 when you take the limit, when you actually write for this particular case, which will be pretty complex, which I plan not really to get along with. Secondly, is that if you consider the case where you want to consider the case ftt, but when you have ftt, that will be corresponding to dt dt, t quadratic variation of this function t, and that will be equal to 0. So, that is why those terms really do not appear in this Ito's formula. So, here the idea is not to give you something very, some very tricky thing, but really to give you some very basic idea of what Ito's calculus is like. And see, these formulas would be very, very useful, and please keep in mind this set of shorthand rules. A very important idea is to understand that this dWt, what I can write from here, I can take it to this side and write it as dWt is equal to f dash Wt dWt plus half f double dash Wt dt. So, that thing is just a shorthand of this. You do not really have stochastic differentials, what you have is stochastic integrals. It is of fundamental importance to remember that there is nothing like a stochastic differential, there is nothing called a differential of a Brownian motion, because Brownian motion is not a differentiable function. So, you cannot define the differential of a Brownian motion. So, since like Wt into dWt, so you cannot define that. What you can define is a stochastic integral, and that is the key. We are essentially talking about stochastic integral. So, Ito's formula, what you see in this Taylor's expansion, they are not written really in terms of derivatives, but in terms of integrals, and that is the key idea that you really have to remember if you want to make a progress. In the next class, what we are going to talk about, we are essentially going to talk about a very general process. So, we were going to talk about a stochastic process, a very general stochastic process called an Ito process. So, here we end this class by describing you what a Ito process is. So, Ito process is a process which consists of the constant x, or so there is a random variable x, xt, a stochastic process xt, and then this xt, sorry, x of t, I write x of t. So, this xt can be decomposed into x0 plus a Ito integral plus a normal integral. So, any Ito process is a stochastic process. So, any stochastic process is called an Ito process. It can be decomposed into 3 different parts. One is x0, the 0th value of the process, plus an Ito integral plus a ordinary Lebesgue integral. If we can do that, then essentially we are talking about something called the Ito process. And what should be the Ito's formula for an Ito process? What should be the quadratic variation of an Ito process? All these things will come in the next class, which you will see very soon. Thank you very much.